Hello and welcome back to the next video lesson. Today we're going to talk about the concept of resistivity. Resistivity is a natural phenomenon that each material experiences. So, let's say we have in this picture here a wire made of a material, which is a conducting material. Depending on what something's actually made of, will determine how much electricity can flow across its surface. So there is a chart on the front page of the reference table. There is a chart on page 4 of the reference table. I have excerpted it here, and I'll show you. Under the electricity title, resistivity is formula E6. And it says that R is equal to this Greek letter rho, which looks like a P, multiplied by the length of the wire, divided by the cross-sectional area of the wire. And I have a little doodle right here to help you see that. The length of the wire, the cross-sectional area of the wire. And so the material that the wire is made of can either be determined, or with that material, aluminum, copper, gold, nichrome, silver, or tungsten, on the Regents reference table, you can determine the resistance on the wire. So let's take a look at the unit of resistivity. It's in ohm meters, so this Greek letter omega times a meter. So these values are for 20 degrees Celsius. So when you read a problem, which we're going to look at soon, you're going to have materials at 20 degrees Celsius. And you will either, like I said before, have to determine the resistivity, or determine the material, or determine the resistance of the wire itself. All right, let's go back to the other slide. Why is this formula equal to R is rho L over A? And why does cross-sectional area come into play here? So if we were to take this tube and unroll it, you get a rectangle. So the area is the length of the wire, and then the circle cross-sectional area stretches out into a straight line here, which is really the circumference, which is 2 pi r. So the formula is used to find the resistance of a piece of wire. Of course, you can always back solve, and one of the common skills that the Regents wants you to do is to either solve for the resistance itself or to solve for the resistivity. But either way, you have to be given 3 pieces of information to find the fourth, because there are 4 variables in this equation. All right, so let's just take a look at some of the laws of resistance based on this formula alone. As the length of the wire increases, the resistance will also increase. So let's take a look at the area, the cross-sectional area of the circle. As the area increases, the resistance decreases. You see it's on the bottom. So it's an inverse relationship, not inverse square, but inverse. It's first a to the first power. So when you have more surface area, there's more room for all of those charges to flow. And of course we have a temperature constraint here. As temperature increases, the R also increases, and that's for metal wires. Now, of course, if you're dealing with nonmetals and solutions, it's actually the opposite. It decreases. But in the Regents curriculum, we don't worry about nonmetals and solutions. This is the main point. As temperature increases, the resistance increases for a metal wire. All right, let's take a look at a problem. Okay, here we have a CASA learning question, which is an old Regents question. And it says, base your answer to the question on the following information in the diagram below. So I picked this particular problem because it has a diagram that you have to interpret, as well as the formula that you have to apply. A 10-meter length of copper wire is at 20 degrees Celsius. The radius of the wire is 1 times 10 to the negative 3 meters. All right, so here we have it. This circle represents the wire that you're looking down at it as if you were looking at the head pencil point. Calculate the resistance of the wire. So we want to use the formula for resistivity. Resistivity is rho, the Greek letter R, which looks like a P, but it isn't. Rho times length divided by area. Now in our particular case, we know that it is a copper wire. So if I look up copper, I see copper is this value right here. So it's 1.72 10 to negative 8 ohm meters. Then I input that and I multiply by the length given in the problem. But here's the little trick. I have to divide by the area. So how do I know what the area is? Well, it's pi r squared. Remember, they gave you the radius of the wire, so I had to take that extra step and calculate the area, pi r squared. And I put that under here. And then when I compute it, I get 5.5 10 to negative 2 ohms. Let's just take a quick look at how the units cancel. So resistivity is ohm meters times meters divided by meters squared. So this meter and this meter multiplied meter squared divided by this one meter squared. So they all cancel out, leaving you with ohms. All right. That is how easy it is to calculate the resistance of a wire based on its length and its material composition. Let's do one more problem where we're going to back solve for resistivity. So here's the information. A 3.5 meter length of wire with a cross-sectional area of 3.14 10 to negative 6 meters squared is at 20 degrees Celsius. The current in the wire is 24 amps when connected to a 1.5 volt source of potential difference. Calculate the resistivity of the wire. This is actually a two-part problem, and I'll show you why. Okay, let's take a look at another problem. We're going to back solve for the resistivity rho. So we're going to go to the resistivity formula, R equals rho L over A, and we're going to input what we have. So we look to see, did they give us a resistance? And according to this solution, it says 6.25 10 to negative 2 ohms times the area divided by the length. But I don't see a 6.25 10 to negative 2. Where did they get that from up here? Well, that's the trick to this problem. You take this current I and this voltage V, and you have to solve for R. So using Ohm's law, R equals V over I, 1.5 volts divided by 24 amps gives you 0.0625 ohms, or 6.25 10 to negative 2 ohms. And so that's where this number comes from. Then you have 3.14 10 to the negative 6 meters squared, which is given in the problem, divided by a length of 3.5 meters given in the problem. And you plug these numbers in, you compute, and you get 5.61 times 10 to the negative 8 ohm meters. Now, even though the problem doesn't ask you what kind of material is this, you can take the rho equals 5.61 times 10 to the negative 8 ohm meters, and you could look this up on your reference table, and you'll find right here 5.6 times 10 to the negative 8 is tungsten. So they could have added an extra part to this problem, and you would have discovered that you were dealing with tungsten. All right. That was a great problem. We'll see you in the next video.